Hello and welcome to this session. In this session, we will continue chapter 1 further. So today's topic is basic property of electric charges. In the last session, we discussed about electric charges. We discussed about charging by induction. So in this session, we will move forward and we will discuss basic property of electric charges. Now, there are three basic property of electric charges. They are additivity of charges, conservation of charges, and quantization of charges. Now we will discuss each of them in detail. First one is additivity of charges. Now additivity of charges implies that charges can be added up like real number, because electric charge is a scalar quantity, so they can be added like scalars. For example, suppose we have a system which contains n charges, q1, q2, q3 up to qn. So we have a system which contains n charges, q1, suppose q2, q3 up to qn. Then the total charge q on the system will be the algebraic sum of all these charges up to qn. So when charges are added, they are added like real numbers because electric charge is a scalar quantity. Now while adding electric charge, one thing that should be kept in mind is that we have to use proper sign while adding them. For example, suppose we have a system of charges, 5 charges having value plus 1, plus 2, minus 3, plus 4 and minus 5. So when we will calculate the total charge on the system, then total charge will be the sum of all these charges. We will simply add the charges, but the sign of the charges should be kept in mind. That is, it will be plus 1, plus 2, minus 3, plus 4 and minus 5. So plus 1 plus 2 is plus 3 minus 3 is 0, 0 plus 4 is 4 and 4 minus 5 is minus 1. So the total charge is minus 1. Our next topic is conservation of charge. Now we have already studied in the previous session that when bodies are charged by rubbing, there is a transfer of electron from one body to another. Means no new charges or no new electrons are created or destroyed. There is just a transfer of electron from one body to another. One of the body loses electron, the other gains electron. Suppose we have two bodies here. So if there is an electron transfer from this body to this body, then here there is a loss of electron. So this body will be positively charged. On the other hand, there is a gain of electrons here. So this body will be negatively charged. So no new charges are created here. There is just a redistribution of charges. Since there is a movement of electron from body A to body B, so body A gets positively charged and body B gets negatively charged. This is called conservation of charge. So we can further explain it as within an isolated system consisting of many charged bodies, due to interaction among the bodies, charges may get redistributed, but the total charge of the isolated system is always conserved. So here we have an isolated system consisting of two bodies. So if there is an interaction between two bodies, say we are rubbing the two bodies, then there will be a redistribution of charges, that some of the electrons will move from body A to body B, but no new charges are being created or destroyed. There is just a redistribution. So charges are neither created nor destroyed. So this is known as conservation of charge. Our next topic is quantization of charge. Now, what is quantization of charge? So, experimentally, it has been observed that the charge on any body, suppose there is a body and it has charge Q. So, this charge will be an integral multiple of the basic charge E. E is the basic unit of charge. So I can write it as Q is equals to NE. Here N is any integer, it can be positive, it can be negative, and the value of E, that is the basic unit of charge, is 1.602192 into 10 raised to power minus 19 coulomb. C stands for coulomb, COULOMB, and coulomb is the SI unit of charge. So this is known as quantization of charge. Now the basic unit of charge, which we have just seen here, E, it is basically the charge on an electron or a proton. That is, E is the electric charge carried by a proton or an electron. So by convention, we know that the charge on electron is taken to be negative. So charge on electron will be written as minus E. So it is minus E, while charge on proton is plus E. Now there is a question. Question is, how many electrons constitute 1 coulomb of charge? If you would remember, this is the question of class 10th electricity chapter. So I hope all of you can find it out very easily, but still here we will do it. Question is, how many electrons constitute 1 coulomb of a charge? Now, we know that charge on one electron is 1.6 into 10 raised to power minus 19 coulomb. This is the value of E. That is the value of basic unit of charge. It is 1.6 into 10 raised to power minus 19 coulomb. So we can write it as 1.6 into 10 raised to power minus 19 coulomb is constituted by 1 electron. So 1 coulomb will be constituted by 1 upon, we are simply doing unitary method here, it is 1.6 into 10 raised to power minus 19. So it is 1 upon 1.6 into 10 raised to power minus 19. So we can write it 10 raised to power 19 goes to numerator, it becomes 10 raised to power plus 19, and here it is 1 upon 1.6. So point is removed, here comes 10, 2 5 times, 2 8 times, so it is 5 upon 8. So I can further write it as 50 upon 8 into 10 raised to power 18. Solving it, 2 4 times 8, 225. So it is approximately equals to 6.25 into 10 raised to power 18. So electrons. So this is a fairly large value, that is 1 coulomb charge will be contained by this much number of electrons. So 1 coulomb is a very large value. It is very seldom that in practical life we encounter a charge of such a big magnitude. Generally, in our practical problems, we deal with charge which is much lesser than 1 coulomb. So we have further small units of electric charge. Just now, we saw that the charge contained, or 1 coulomb of charge is contained by about 6 into 10 power 18 electron, which is a huge number. So as I have told you already that charges of this large magnitude are seldom encountered, so we use smaller units. So we have two smaller units. First is 1 millicoulomb, which is 10 raised to power minus 3 coulomb, and second is 1 microcoulomb, which is smaller than millicoulomb. 1 microcoulomb is equal to 10 raised to power minus 6 coulomb. Now there is a very important question. Can quantization of charge be ignored while dealing with macroscopic charges? In other words, I'll put this up. Is quantization of charge, the concept of quantization of charge, is it valid everywhere, or is it useful everywhere, or is it important everywhere? So see, at the macroscopic level, we deal with the charges that are enormous compared to the magnitude of charge, that is E. We have just we just know that E is 1.6 into 10 power minus 19 coulomb. So suppose a charge of 1 microcoulomb contains about 10 power 13 times the electronic charge. So at this scale, the fact that the charge can increase or decrease only in units of E is not very different from saying that the charge can take continuous value. So let me explain you. Suppose I have an object, and this object contains 1 microcoulomb of charge. Now 1 microcoulomb is, as we already know, it is equals to 10 raised to power minus 6 coulomb. Now it can also be written as 10 power 13 times the basic unit of charge E. So if an object has a charge of 1 microcoulomb, then approximately it has a charge equals to 10 raised to power 30 electrons. Now that is a very huge number. If the charge of this object is increased by, suppose, we add one more e, then again one more e, then again one more e, then that is not going to change this value by a large amount. So we can say that at the macroscopic level, the quantization of charge has no practical consequence and it can be ignored. So we can compare the situation. Suppose I make a dotted straight line, and if this dotted straight line is viewed from a very large distance, then it will appear to be a continuous line. But the reality is that it is not continuous. Since we are viewing it from a very large distance, so it will appear to be continuous, but it is actually not continuous. So same thing happens in case of macroscopic objects or at macroscopic level. If the charge is increased by the multiples of E, or it is decreased by the multiples of E, then it is no longer discrete, it is assumed to be continuous. So I hope this concept is clear. So again we'll come back to our question, can quantization of charge be ignored while dealing with macroscopic charges? Yes, we can ignore the quantization while dealing with macroscopic charges, because at macroscopic level the increase by integral multiples of E has no practical change. So yes, it can be ignored. The answer is yes, we can ignore the quantization of charge. I hope this concept would be clear by now. So now we will solve a question. It is an example of NCERT. The question is, if 10 raised to power 9 electrons move out of a body to another body every second. Suppose we have two bodies, and from this body to this body, 10 raised to power 9 electrons are moving per second. So if 10 raised to power 9 electrons move out of a body to another body every second, then the question is asking how much time is required to get a total charge of 1 coulomb on another body or other body. So in simple terms, the question is asking that how much time will it take for a transfer of 1 coulomb from this body 1 to this body 2. So I hope the question is clear. The question is asking simply that find the time which will be taken for the transfer of 1 coulomb of charge from body 1 to body 2. So first we will find out that if 10 power 9 electrons are getting transferred from body 1 to body 2 in 1 second, then how much charge does they actually carry from body 1 to body 2? So we know that charge on one electron is minus 1.6 into 10 raised to power minus 19 coulomb. So charge on 10 power 9 electrons will be this value multiplied by 10 power 9. So it is negative of multiplied by 10 power 9. So it will become negative of 1.6 into this will become 10 raised to power minus 10. So this is the amount of charge which is getting transferred from body 1 to body 2 in 1 second. So now we can say that 1.6 into 10 raised to power minus 10 coulomb charge is transferred in 1 second. So 1 coulomb charge will be transferred in this simple unitary method. It is 1 upon 1.6 into 10 raised to power minus 10. If we will solve it, then it will become 1 upon 1.6. This will become 10 raised to power plus 10. If we will move it to numerator, so removing the point, we have 10 by 16, so it is 5 by 8, so it is 50 upon 8 into 10 raised to power 9. So it will become 6.2 into 10 raised to power 9 seconds. Now just to give you an idea what this value of time is, it is seconds. Now to convert it into, so it is seconds, so to convert it into hour, I have to divide it by 60 into 60. Dividing by 60 will convert it into minute, and then further dividing by 60 will convert it into hour. Now since one day contains 24 consists of 24 hours, so I'll multiply here 24. So now we have the value in days. Also uh, supposing that the number of days in a year is 365, so now the value which we will get here will be in years. So if you will solve it, the value if you will solve it, the value will approximately come out to be 198 years. So if 10 raised to power 9 electron moves out of a body to another body every second, you know that 10 raised to power 9 is a very big value. So even if electron move from one body to another body at the rate of 10 power 9 electron per second, then still it would take 198 years. 198 years is a very large period of time. So it will take 198 years for the transfer of 1 coulomb. So again I have shown here that 1 coulomb is a very large value. For practical purpose, we generally deal with 1 microcoulomb and 1 millicoulomb, which I have already told here. So I hope this concept would be clear. So now we will solve another question, example 1.3 of NCERT. The question is, how much positive and negative charge is there in a cup of water? So let's begin from here. If we take one molecule of water, so one molecule of water, that is H2O, how many protons and electrons does it contain? Actually, see, we have been asked how many positive and negative charge. We know that positive charge is carried by proton and negative charge is carried by electron. So if we can calculate the number of protons and the number of electrons in a cup of water, then our question is solved. So our first priority is to find out the number of protons and number of electrons in 1 cup of water. Then when we will get the number of protons, then we will multiply that value with the charge on each proton, and then we will get our value very clearly. So first we have to find the number of protons in a cup of water. So let us assume that let us take that uh, let us assume a cup of water is 1 cup of water has suppose 250 grams of water. We have just assumed that. Now we need to find how many molecules of water is there in 250 gram of water. So we know that the molecular mass of water is, so a hydrogen, the molecular atomic mass of hydrogen is 1. We have 2 hydrogens, so it is 2 into 1, plus the atomic mass of oxygen is 16, so we have 16, so it comes out to be 18. The molecular mass of water is 18. So now we have to find the number of molecules present in 250 gram of water. So we know that 18 gram of water will contain 6.02 into 10 raised to power 23 H2O molecules. This uh, we have studied in mole concept either in class 9th or class 11th. We must have studied it, that 1 mole of anything contains 6.02 into 10 raised to power 23 number of particles. Also, 1 mole of any substance is equal to its molecular mass in grams. So 18 gram of water will contain 6.02 into 10 raised to power 23 H2O molecule. So 1 gram of water will contain 6.02 into 10 raised to power 23 divided by 18. We are just dividing it by 18. So we have to find out the number of molecules in 250 gram of water. So it will be 6.02 10 raised to power 23 upon 18 multiplied by 250. So this is the number of molecule of water in 250 gram of water. So now one molecule of water has, so we can see here, one molecule of water contains 2 hydrogen and 1 oxygen. So 2 hydrogen will have 1 proton each, since the atomic number of hydrogen is 1, so it will have 1 proton, and atomic number of oxygen is 8, so it will have 8 protons. So since we have 2 hydrogens, so we'll have 2 protons, and then we have 1 oxygen, then we have 8 protons. So 1 molecule of water will have 10 proton and 10 electrons. So 1 molecule will have this much amount of proton and electron. So charge, since see, in the water is a neutral compound, so the positive and the negative charge will be equal. So we can find out either, if I'll find out the positive charge on uh, positive charge in one molecule of water, then positive charge in one molecule of water will be, uh, since it has 10 protons, so 10 multiplied by 1.6 into 10 raised to power minus 19, because the charge carried by one proton is 1.6 into 10 raised to power minus 19 coulomb. So for 10 proton it will be 10 multiplied by 1.6 into 10 raised to power 19. So the number of, it is the charge carried by one molecule of water. So total number of molecules is this. So total charge carried will be the product of this and the product of this. So it will approximately, if we will multiply these two, it is the charge carried, the positive charge carried by one molecule, and this is the total number of molecule. So if we multiply both of them, it will come out to be around 1.34 into 10 raised to power 7 coulomb. So this is the positive charge carried by a cup of water, assuming that a cup has 250 grams of water, and the same amount of charge will be the negative, or same amount of charge will be negative in a cup of water. So as water is a neutral compound, already I have said, so the total charge will balance out each other. So I hope it is clear. I'll go through it once more. The question is, how much positive and negative charge is there in a cup of water? So firstly, we will find out how much number of molecule water is there in a cup of water. So we have assumed that a cup of water contains 250 gram of water, and we know that the molecular mass of water is 18 gram. By mole concept, 1 mole of water is equal to the molecular mass in grams. Also 1 mole is equal to 6.02 into 10 raised to power 23 number of water molecule. So here 18 gram of water molecule is equal to 6.02 into 10 raised to power 23 H2O molecules. Further solving, we arrived at the number of molecules of water contained in 250 gram of water. So now we know that one molecule of water has 10 proton and 10 electrons. How we concluded this? Because the formula of water is H2O. It contains two hydrogen. Each hydrogen has one proton, so two hydrogen will have two protons, and it contains one oxygen. The oxygen has 8 protons. So total number of proton is 10. Now, as what is the neutral compound, so the positive and negative charge will be same. So we'll find either of, we can find either of it. So the positive charge on one molecule of water is, since one molecule of water contains 10 protons, so the total positive charge will be 10 multiplied by 1.6 into 10 power minus 19. 1.6 into 10 power minus 19, 1.6 into 10 power minus 19 is the value of charge carried by a proton. So this is the total charge on one molecule, and this is the total number of molecules. Multiplying both of them, we get the total charge in a cup of water.